Hello everyone, welcome back to my video lecture series on Introduction to the Finite Element Method in 1D. In the previous lecture, we discretized the weak form of the Poisson's equation in 1D, and at the end of that, we realized that the approximate solution UH of x to the Poisson's equation can be expressed as summation dB nb plus g multiplied by nn plus 1 into of x. Here, the functions nb are the basis functions. Our goal in this video lecture series is to solve the Poisson's equation in 1D using the linear finite element method. When using linear elements, we essentially assume that the approximate solution UH of x is a piecewise linear function. We begin by splitting our domain, which is from x equal to 0 all the way up to 1, into n elements. We thus end up with n plus 1 nodes. So the first node x1 has to be equal to 0. The next node is x2, x3, and so on all the way up to xn, and finally xn plus 1. The last node xn plus 1 has to be equal to 1. Note that element 1 ranges between nodes x1 to x2, element 2 includes nodes x2 to x3, and so on. Within each element, the function is assumed to be linear. Now let's consider a particular element, say element A. So element A must range from node XA all the way up to node XA plus 1. Within this element, the solution is assumed to be linear, and let's say that the value of the solution at XA is UA, and the value of the solution at XA plus 1 is UA plus 1. Now we know that the approximate solution UH of x can be expressed as some constant alpha plus beta multiplied by x, since it's assumed to be linear within this element. So this relation holds true for x belonging to xa, xa plus 1. Now how do we determine what these constants alpha and beta are? So we know that at xa, the value of the solution is assumed to be UA. So UH evaluated at x equal to xa, which is equal to alpha plus beta times xa, is equal to UA, whereas UH evaluated at x equal to xa plus 1, which is equal to alpha plus beta times xa plus 1, is equal to UA plus 1. So we now have these two equations for two unknowns, alpha and beta. So we can solve the system of equations, determine the values of alpha and beta, and substitute them into this equation UH of x equal to alpha plus beta of x, and that will give us what the approximate solution looks like within this particular element. So when we do so, what we end up with is the following relation. UH of x is equal to xa plus 1 minus x divided by xa plus 1 minus xa plus UA plus 1 into x minus xa divided by xa plus 1 minus xa. As a quick sanity check, let's just see if this expression looks right. So now at x equal to xa, this second term over here will be 0, this term will be 1, so UH of x will be UA, which is exactly what we assumed right here, whereas at x equal to xa plus 1, this term over here, the first term will go to 0, the second term, this part over here, will be 1, and so UH of x at x equal to xa will be nothing but UA plus 1, which is exactly what we had considered. So this is a correct expression for UH of x within this particular element. What's interesting is that we can see that if you call the first term over here as na, a function of x, and the second term over here as na plus 1 of x, another function of x, then this form over here looks very similar to the finite element form that we had derived previously. So essentially that's telling us that UH of x can be written as a linear combination of some basis functions na of x and na plus 1 of x. So based on this relation, we can now define the basis functions for the piecewise linear finite element domain as na of x is equal to x minus xa minus 1 divided by ha minus 1 Here HA minus 1 is the width of the element number A minus 1, which is equal to XA minus 1. And this holds true for element number A minus 1, that is x belonging to XA minus 1 all the way up till XA. NA of x is equal to XA plus 1 minus x divided by HA, and this is true for element number A, which ranges from x belonging to XA all the way up till XA plus 1, and NA of x is 0 for all other values of x, so otherwise. Now this relation holds true for A equal to 2, 3 all the way up to n, and as I just mentioned, here HA is the width of element number A, so that can be written as XA plus 1 minus XA, and similarly HA minus 1 is the width of element number A minus 1, so it can be written as XA minus 1. So this right here is the definition of the basis function for the piecewise linear finite element domain. Now at the boundary, we have similar basis functions, but they are one-sided. And so we have n1 of x defined as x2 minus x divided by h1, and this is true for x belonging to x1 to x2. So basically this relation over here, and at the other boundary we have n plus 1 of x defined as x minus xn divided by hn, and this is true for x belonging to xn all the way up till xn plus 1. So these are the one-sided basis functions defined at the boundaries. Now where does this expression or definition come from? So if you notice, NA of x is defined for two particular elements, element A minus 1 and element A. So at element A, the relation is this one, which you can notice is the same as this term over here, which we just got. And for element A minus 1, the expression is this one, which is pretty much the same as this relation over here. So this is the motivation for this particular definition of the basis function. At the boundary, we just have one particular element, not two elements, and that's why we have one-sided basis functions. Now let's try to plot these basis functions to get a better sense of what they look like. So firstly, we have our domain ranging from 0 all the way up to 1. So in general, let's consider element A, which is ranging from XA all the way up till XA plus 1. And similarly, we have element A minus 1, which ranges from XA minus 1 all the way up till XA. Now if you look at NA, then the basis function NA for element A, if you evaluate it at x equal to XA, then this relation over here is going to be equal to 1 at NA of XA. On the other hand, if you evaluate the relation at XA plus 1, then this relation over here is going to be 0. So the basis function is 0 at XA plus 1, and the basis function is 1 at XA. So in general, this is how the basis function is going to look like. It's going to be linear, and it will be 0 at XA plus 1 and 1 at XA. Similarly, if you evaluate the basis function for element number A minus 1, then this term over here is 1 at XA, and this term over here is 0 at XA minus 1. So this is what the basis function would look like for element number A minus 1. So essentially the basis function NA looks like a hat, and so sometimes it is also called a hat function. You can notice that NA of x is a hat centered at XA, it's equal to 1 at XA, and it is 0 at the next two nodes. Similarly, if you plot the basis function NA plus 1, it will look again like a hat, but this time centered at XA plus 1. Whereas if you plot the basis function NA minus 1, it will again be a hat, but this time centered at XA minus 1. This is what NA minus 1 looks like. At the boundaries, we only have one-sided basis functions. So let's say this is x1 equal to 0 and this is x2. Then we will just have a one-sided basis function that looks like this, which was n1. Whereas at the other boundary, say we have xn over here and the last node xn plus 1 equal to 1 over here, then this is what the last basis function look like. It will be n plus 1. So n1 is this relation over here, whereas the basis function nn plus 1 is this equation over here. So based on this particular visualization, we can now make a few observations about our definition of these basis functions. So let's make a few notes. The first observation that we make is that if we consider the basis function na of x, then you can notice that na of x is pretty much 0 in most of the other elements. It is only non-zero in two elements. Firstly, in this element over here, which is element number a minus 1, ranging from xa minus 1 to xa. And secondly, this element over here, which is ranging from xa to xa plus 1, element number a. So na of x is non-zero only in element numbers a minus 1 and a, and it is 0 in all other elements. So essentially, the way we define our basis functions in the finite element method is that they are locally defined, or they range over a finite, they are non-zero over a finite number of elements only, and they are 0 in all other elements. As a result of this, if you focus on one particular element, let's say element number a, which ranges from node xa to node xa plus 1, and within this particular element, you can notice that there are only two basis functions which are non-zero. Firstly, the basis function na, and secondly, the basis function na plus 1. Apart from that, all other basis functions are 0 for this particular element. So our second observation is that within element a, only two basis functions are non-zero, and they are basis functions na of x and na plus 1 of x. All other basis functions are 0 within this particular element, and hence if we try to express the solution within this particular element, then uh of x can be written as na of x multiplied by dA plus na plus 1 of x multiplied by dA plus 1, and this is true for x belonging to xa to xa plus 1. So how do we get this? So we know that in general, of x can be written as summation dB nb plus this second term over here. But we know that within this particular element, pretty much most of the basis functions are 0. So the only thing that is remaining in summation dB nb are dA multiplied by na and dA plus 1 multiplied by na plus 1, the only two non-zero basis functions. And that's how we get this relation. I would point out here is that if you look at this particular expression for of x within element A, then that is pretty much the same as what we just derived over here for element A, which is ua multiplied by na plus ua plus 1 multiplied by na plus 1. So just to kind of check that that's what we had derived previously as well. The third observation that we make is that if we try to evaluate the basis function na of x at some particular grid point xb, then this can be written as delta ab, which is basically equal to 1 if a is equal to b, and it is equal to 0 if a is not equal to b. So if you look at na of x, then we know that na of x is equal to 1 at grid point xa, but if you evaluate it at any other grid points, then it is basically equal to 0. And that's why na of xb can be written as delta ab. Now, in general, we know that the solution of x at some arbitrary x can be written as summation dB nb of x, or b ranging from 1 up till n, all the n basis functions, plus an extra term for the Dirichlet boundary condition. Now what's interesting is that if you take this relation and put it into this equation, then what we will end up with is that evaluated at a grid point xb is nothing but dB. Now why is that? So if you evaluate of x at one particular grid point, then within all of these terms, pretty much most of them will be 0 because of this relation over here. The only term remaining is dB multiplied by 1, and thus UH of XB is equal to DB. So what this tells us is that in this relation UH of X equal to summation DB NB, the constants DB are nothing but the value of the approximate solution UH of X at the grid point XB. So DB is UH of X at XB. So essentially what this relation is doing is that it is telling us how to interpolate the solution X for points in between the grid points where the solution is known and is equal to DB equal to UH of XB. And this is why our basis functions are also called interpolation functions. Since our basis functions are essentially helping us interpolate the solution in between the grid points. And at the grid points, the solution is nothing but the constants, which are the weighting factors for these basis functions. Another observation that we can make is that this relation over here, UH of X equal to NA dA plus NA plus 1 dA plus 1, is exactly the same as this relation over here, which we derived initially, UH of X equal to UA NA plus UA plus 1 NA plus 1, because now we know that UA, the solution at grid point XA, is nothing but equal to dA, whereas dA plus 1 is exactly equal to UA plus 1, which is the solution at grid point XA plus 1. So that's a nice verification that we can now make. Finally, another thing that I would note is that if you recall, we were trying to solve the matrix equation KD is equal to F. Here K was the stiffness matrix, D was the unknown vector, and F was the forcing vector. And here the D vector consists of all of these constants dB, and we know that dB is nothing but the solution at the grid point. And so when we solve this matrix equation, what we are doing is we are actually solving for the solution at the grid nodes. This is why the unknown vector D is called the displacement vector, because it is actually representing the displacement or the solution at the grid nodes, not just the constants for the weighting for the basis function. So the last topic that I want to cover in today's lecture is the comparison of a local versus a global description of an element. So for a minute, let's say we are solving a 2D finite element problem, and in that case, let's say we have some 2D element which looks like this. So the element has 4 nodes and it's of a regular shape, as you can see over here, and this is what it looks like in the XY coordinate system, which is our global coordinate system. Now, if you want to evaluate the stiffness matrix for this particular element, then we need to perform an integration over this irregular shape, which can be quite tedious. And hence, for simplicity, we often map this global coordinate system into a local coordinate system where we map it to a more regular shape, let's say a square, and say the square has a width of 2. So this node is at -1, -1, and this particular node is at 1, 1. And the axis for this local element are, let's say, psi and gamma. So this right here is the local description. Now when we do something similar for a 1D element, then in the global domain, we know that, let's say, element number A has 2 nodes. The nodes are XA and XA plus 1. Within this particular element, we have 2 basis functions which are non-zero, and they are basis functions NA and NA plus 1. And the solution within this element we know is assumed to be linear, and let's say it looks like this, with value dA at XA and value dA plus 1 at XA plus 1. Now when we map it into a local domain, then the local domain is assumed to be from -1 to +1 for simplicity. Within the local domain, we again have two basis functions, and those basis functions are denoted as n1 of psi and n2 of psi. And the solution again is linear, and the value of the solution at -1, the first node, can be noted as d1e, and the value at the second node, 1, can be denoted as d2e. Now I would note that d1e is nothing but the same as dA, and d2e is exactly the same as dA plus 1. It's just that this notation donates this notation tells us that we are looking at a local description. Another point, so xa, the first node within this element, can be described as x1e, whereas xa plus 1, the second node within this element, can be denoted as x2e from the element's perspective. Now we know that in the global description, the solution can be written as follows. So in the global description, the solution within this particular element, UH of x, can be written as dA multiplied by NA of x plus dA plus 1 multiplied by NA plus 1 of x. The same expression can be written in a local description as UH evaluated at psi of x, where psi is the local coordinate, is equal to d1e multiplied by n1 of psi and plus d2e multiplied by n2 of psi. So what are these local basis functions n1 and n2? So n1 of psi is given by half multiplied by 1 minus psi, whereas n2 of psi is given by half multiplied by 1 plus psi. Now how do we get these particular relations? So we know that both n1 and n2 are both linear, and so they can be written as, say, alpha multiplied by psi plus beta for some constants alpha and beta. Now for n1 of psi, we know that at psi equal to -1, n1 is equal to 1, whereas at psi equal to +1, n1 is equal to 0. Using these two relations, we can determine the values of alpha and beta and then get the expression for n1 of psi, which is given by this relation over here. And similarly, n2 of psi is given by this relation over here. Just to verify, let's look at n1 of psi, and you can see that if psi is 1, then this equation is 0, whereas if psi is -1, then this expression is equal to +1, which is exactly what we expected it to be. The last thing that we need to know is that how do we get the mapping from x to psi or psi to x? For example, mapping from x to psi or psi to x. So in general, we know that this mapping is linear. So let's say psi of x can be written as a linear function of x. So let's say it is alpha plus beta times x for some constants alpha and beta. Additionally, we know that psi evaluated at x equal to xa, which is alpha plus beta times xa, has to be equal to -1 because xa has been mapped to -1. So this is equal to -1. Similarly, psi evaluated at xa plus 1, which is alpha plus beta multiplied by xa plus 1, has to be equal to +1 because the node xa plus 1 has been mapped to +1. Now these are two equations for two unknowns alpha and beta. We can solve them to determine alpha and beta and then substitute them into this particular relation over here. And if you do that, what you get is psi of x is equal to 2x multiplied by xa, or 2x minus xa minus xa plus 1 divided by ha. If we manipulate this relation, we can get the inverse mapping x of psi as ha multiplied by psi plus xa plus xa plus 1 divided by 2. Now this can be simplified as half multiplied by psi times xa plus 1 minus psi times xa, because HA is xa plus 1 minus xa, plus xa plus xa plus 1, which can be further expressed as xa multiplied by 1 minus psi by 2 plus xa plus 1 multiplied by 1 plus psi by 2. Now what's remarkable is that you notice that 1 minus psi by 2 is nothing but n1 of psi, whereas 1 plus psi by 2 is nothing but our second basis function n2 of psi. So what we have just shown is that the mapping x of psi, which takes us the local variable psi and converts it to the global variable x, can be written as xa multiplied by n1 of psi plus xa plus 1 multiplied by n2 of psi, which can also be written as summation a equal to 1 to 2 xae and a of psi. So the way we get this is that we know xa is denoted by x1e and xa plus 1 is denoted by x2e from the local element perspective. So this right here is the relation or the mapping from the local coordinate psi to the global coordinate x. And what's remarkable is that the mapping again involves our basis functions, and that's why our basis functions are also called shape functions, because they help us convert an irregular shape in the global coordinate to a more regular shape in the local coordinate. So to summarize, what we have learned so far is that there are three interpretations for our basis functions. Firstly, these functions are basis functions. And so if you recall, the test function w of h can be written as a linear combination of these basis functions. And similarly, the solution uh of x can also be written as a linear combination of these same basis functions. The second interpretation is that they are interpolation functions. Now we know that uh evaluated at some grid point xb is nothing but dB. So these constants dB are the solution at the grid points, and thus this relation is telling us how to interpolate the solution in between the grid points, and hence the basis functions are also called interpolation functions. And finally, the third interpretation is that these basis functions are also shape functions, because they also define the mapping from the local coordinate psi to the global coordinate x. So these are the three interpretations of these basis functions. Now that we have defined what the basis functions are, all that is left to do is to take these definitions of the basis functions and substitute them into the matrix equations to then determine the solution. We'll do that in the next lecture. Thank you for listening, and I hope you learned something.